In this video, we're going to cover the heart of this unit, this module, and talk about the quantitative analysis of reactions. We're basically going to talk about the three basic types of stoichiometry problems that you're likely to face in this class or any other chemistry class, and hopefully by the end of this you'll have a clear idea of how to approach those problems. So our learning goal is to develop methods for solving stoichiometry problems. There are three types of stoichiometry problems that are prevalent, and really they constitute the vast majority of the ones you're likely to run into. The first one I'm going to call a moles to moles problem. Now for each of these types I'm going to specify three different things. I'm going to specify what I have, that is, what are you given in the problem, what I want, what is it you're asked to produce in the problem, and what you need, that is the conversion factors that you might need to solve the problem. So in a moles to moles problem, what you are given are the number of moles of one of the things that's in the reaction. You're going to be asked to produce the number of moles of one of the other things in the reaction, either something that's reacting with it or something that's produced by it. And then what you're going to need is the mole ratio, which is simply the ratio of the coefficients from the balanced chemical equation. The second type of problem that you may run into is moles to grams. In this case, what you have is moles of one of the species. You're going to be asked to produce the number of grams of another species, and what you're going to need is both the mole ratio and the molecular weight of the species that you need to report in grams. Finally, the third major type is a grams to grams problem. And in this case, what you have is grams. What you're going to want is to produce grams of another species, and you're going to need both the formula weights of the species that you are given and the species that you need to produce, and in between you need the mole ratio that connects them. Now I should mention that there are some variations on these problems. For example, you could go from grams to moles, but it's essentially the same thought process for the moles to grams, so I'm not going to cover that one specially. Now we're going to illustrate these three types of problems using one reaction for all of them. That's the combustion of ethanol that produces carbon dioxide and water. So first we'll start with a moles to moles conversion, and the problem might be something like how many moles of water are produced if a certain number of moles of ethanol, 0.562, is consumed. So in this case, what I have is the 0.562 moles of ethanol. What I want is the number of moles of water. So now the conversion factors that I need to get from one to the other is essentially the mole ratio. In order to go from moles of ethanol to moles of water, all I need is the mole ratio, which I can get from the balanced chemical equation listed up at the top. So when I write this out, I start with 0.562 moles of ethanol. That's what I was given. The conversion factor is going to convert from moles of ethanol to moles of water, so it's going to have to be moles of water divided by moles of ethanol. I look at the balanced chemical equation and I see the number in front of the water is 3, and the number in front of the ethanol, it doesn't actually have a number, so it's 1. So that ratio is going to be 3 to 1. When I plug that in and multiply it out, I'll get 1.69 moles of water. So that should be the answer you get. Okay, notice that the conversion factor here, the only one we have, is the mole ratio. Now here's a chart that shows you kind of how to conveniently lay these things out. In this chart, A is the thing that you're given and Z is the thing that you need to find. And that's always going to be true in these charts. So the conversion factor is only one that's in the middle, and it comes from the balanced equation coefficients. So it's moles of Z to moles of A. So this chart shows you that you would cancel moles of A and you would be left with moles of Z for your output. All right, let's go to the next type, moles to grams. Now we're going to say if we use 0.96 moles of oxygen in the combustion of the ethanol, how many grams of carbon dioxide are produced? So we're going from moles of oxygen to grams of carbon dioxide. So what I have is the moles of oxygen. What I want is how many grams of carbon dioxide are produced. And the conversions I'm going to need are first to go from moles of oxygen to moles of carbon dioxide, then to grams of carbon dioxide. In all of these problems, I am going to have to make a moles to moles conversion at one point or another. It's the only way I can go from one species to another. Here I'm doing it first, then I'm converting moles to grams. So that first conversion again needs the mole ratio from the balanced chemical equation, and the second one I'm going to need the formula weight for carbon dioxide. So here is the organization chart that I would need. You can see, again in blue, the mole ratio is featured there with the balanced equation coefficients, converting me from moles of A, which is moles of oxygen, to moles of Z, which in this case is moles of carbon dioxide. Then I'm going to convert those moles of Z using the formula weight of Z to grams of Z. So this is the way it would look like if I wrote it out mathematically. I'm starting with 0.936 moles of O2. The mole ratio from the balanced chemical equation is 2 moles of CO2, that's the coefficient in the equation, divided by 3 moles of O2. 3 is the coefficient for oxygen. Then I got to multiply by the formula weight for the carbon dioxide, which is 44.01 grams per 1 mole of carbon dioxide. And if I do all of this multiplication and division, I would end up with 27.5 grams of carbon dioxide. Now, our last type of problem is a grams to grams, and this is the one that involves the most work because it has 3 conversion factors that we're going to have to put to good work. So now I'm going to suppose that I'm burning 14.28 grams of ethanol, and I want to know how many grams of carbon dioxide I'm going to produce from that. So what I have is the grams of ethanol. What I want is the grams of carbon dioxide. So the conversions I need are to go from grams of ethanol to moles of ethanol. Then I can go from moles of ethanol to moles of carbon dioxide. Then I can finally go to grams of carbon dioxide. So the conversion factors are first the formula weight of the ethanol, then the mole ratio that comes from the balanced chemical equation, and finally the formula weight of the carbon dioxide. So the organizational chart would look something like this. I'm going to start with grams of ethanol. I'm going to need to convert those grams into moles of ethanol by taking 1 mole of ethanol is equal to its formula weight in grams. Then I'm going to use the mole ratio, the ratio of the coefficients from the balanced chemical equation, to convert to moles of Z, or in this case, moles of carbon dioxide. And then I'm going to use the formula weight of carbon dioxide to convert it from moles to grams. So here's what it looks like mathematically. I start off with 14.28 grams of ethanol. I'm going to divide by its formula weight, 46.08, so that I can convert from grams of ethanol to moles of ethanol. Then I'm going to use the balanced chemical equation. I have 2 moles of CO2 for every 1 mole of ethanol, so it's a 2 to 1 mole ratio. And then I'm going to multiply by the formula weight of carbon dioxide, 44.01, and when I get through doing all these multiplying and dividing, I'm going to end up with 27.28 grams of carbon dioxide. So the conversion factors are, here's the formula weight for ethanol, here's the mole ratio from the balanced chemical equation, and here's the formula weight for carbon dioxide. So this has been a quick run through 3 different types of stoichiometry problems, but hopefully this is going to help you organize your thoughts so you can solve any of these problems in the future.